So our last point in the previous lecture was this statistical interpretation of entropy, and I think we had discussed that to enough details. I mean, there are many things which can be said about this, but I don't think that's the focus of this course. So the next section is 6.9. Which is entropy rate balance for control volumes. And this should not be a big problem because if you remember in previous chapters, we had energy balance equations for closed systems. And then when we wanted to rewrite those equations for control volumes, all we need to add was the terms associated with mass transfer. So we have to do something similar here. If you look at this equation 6.34, this one, this is something which you need to add, this one. Yeah, so apart from this these two terms, or actually they're not two terms, there are many terms because of the summations, so you have to sum over all the inlets and all the exits. Other than that, it's just standard rate of change of entropy, yeah, for the control volume. Then this will have a contribution from heat transfer. So this is entropy transfer associated with heat transfer. This is the entropy production rate arising from the irreversibilities within the system, or here within control volume to be more precise. And now because the system is now open, that's why you use the term control volume. So at the boundary, you will have mass transfers as well, in and out. So at all those inlets, yeah, at every inlet I, you will have some mass transfer. So if I write that as m dot for transfer, I for that particular inlet, so I can now multiply this with the specific entropy. Yeah, because whatever matter is crossing the boundary, matter has entropy. So if I use small s for the specific entropy without this dot, yeah, I mean that dot is important because dot simply means that it is now crossing the boundary. Yeah. Remember this dot should not be confused with this derivative. This derivative is the rate of change within the system, and that has nothing to do with the boundary. These dots, this q dot, this m dot, this m dot, this represents something crossing the boundary, and this dot again is the rate of change of sorry, not rate of change, the production, entropy production within the system. So this dot is also not something happening at the boundary. These are the boundary phenomena. Okay. So I think I'm leaving this part, integral form. This is needed only when you want to calculate the total entropy. And all you need to do is to integrate. I mean, this is something very easy for you. Small s, remember, is the specific entropy. Yeah? So that small s, if you multiply that with mass, dm, and then you integrate this, then you should get the capital S, entropy. And because m, we know, dm is rho times dv. Rho is density, v is volume. So you just rewrite that. These equations are not the focus of this course. Yeah? They are needed in serious design for mechanical engineers. And we know we are focusing only on basic principles. So we want to get as many basic concepts from this course as possible. So if you now look at this that equation again for the control volume, And if you want to consider this in the steady state, what will happen? In the steady state, this left-hand side will be 0. So you can rewrite the right-hand side by writing everything related to the inlet on one side, everything related to the um, outlet on the other side, or maybe, yeah. So this is actually the modified form. So okay. Uh, is this disturbing you? These sounds? Can you hear the sound, the background sound now?
No, sir.
Okay, you cannot hear that. Okay, because probably some wedding, I don't know, whatever is going on. So I hope you're not getting disturbed by that. Mm. So okay, I think this is just a reminder. These two equations. So I think this is the mass. So if you have a steady state, in the steady state you can write three equations now. So I think this one and this one. This is the mass balance, or to be more precise, mass rate balance. Yeah, because the dates you have rates, and then you have energy rate balance. Yeah, from the first law of thermodynamics. This is pretty standard. We did this, and that's why these are from taken as it is from chapter 4. Yeah, so chapter 4, mass balance, mass rate balance, energy rate balance, and you just want to add this new equation to that dictionary of rate equations, and this is now the entropy rate balance in the steady state. Remember, this 0 means steady state. Yeah, and this is just the right hand side from the previous equation. So that's also, and if you want to rewrite, I mean, have a simple form for one let, one exit, it will be much simpler. You see, instead of that summation, you will just have one S for inlet, one S for output, for outlet. So S1 is for inlet, S2 is for outlet. It's that simplified equation. Um, so if you have this simplified the picture of one inlet and one exit, then you can rewrite this equation uh, to have an expression for S1 for S2 minus 1. This is S1 minus S2, and now you can bring that to the other side. It will become S2 minus S1, divide everything by m dot, and you have this thing on the right hand side. So if you want to have an expression for the um, change in entropy from inlet, let's say 1 represent the inlet, 2 represent the outlet. So during this, the entropy change will have that expression, and you can make sense of it as well. The entropy change has a contribution from all the uh, yeah, from all the um, heat transfers and the irreversibilities. Okay, and because it's small, so it's per unit mass. That's not a big deal. Okay, so as a standard example, there is nothing tricky about this example 6.6. I mean, you can read this in detail when you're done with this lecture. I will only focus on this diagram. So maybe if you look at this, you have a control volume, yeah, and one inlet, one exit. So simplified picture. The boundary temperature is given, yeah, because you know the boundary temperature is needed for writing the equation for entropy. And on this side, you are given pressure, temperature, volume. No, not volume. Sorry, this is the velocity, yeah, 116 meters per second, and temperature at the outlet T2 is given, velocity is given, and you can see that the velocity has decreased, and the phase is given, so it's saturated vapor. It's saturated vapor, and it must be written. Um, so saturated vapor exits at the inlet side. Yeah, steam. So it's written there. So you can write here for your convenience that at the inlet I have steam. Yeah. Which must be superheated because steam is something which we use for superheated. So you have superheated water, and here you have saturated vapor. So everything is given here, and you now it's steady state. So this, of course, you have to rewrite everything for steady state, simple equations. Work, because this is a turbine, so you can expect this to develop work. Now, work developed by this turbine per unit mass transfer is 540 per unit mass. Can you see anything wrong with this equation on the left hand side? What's wrong with the left hand side with this? No, I think there's nothing wrong. That's correct because the unit outside it is kilojoules per kilogram. Yeah. So if this was, let me rewrite this. If this was WCV dot, WCV dot is the work developed by the turbine per unit time, and if you divide this by m, this will only be per unit mass, but it will still be the rate. But if you divide this by dot, m dot, because of these two dots, the result is now work transfer per work developed per unit mass. You can also call it specific work. But specific work is not a good terminology because we use specific. The adjective specific is used for properties. Work is not a property. So it's better to say work developed per unit mass. And you remember this division by m dot is not a coincidence. Yeah. Because when we write the energy balance and the entropy balance, and those you know that you have that summation over all the inlets, summation over all the exits, and you have m dot there, mi dot, me dot, and then multiplied by something. So it is that m dot with which you divide the whole equation, and that's why you have this m dot. So don't expect m here anyway. So now the question here, I mean, what you are supposed to calculate here is the rate at which the entropy is produced within the turbine per kilogram of steam flowing. So which means that here you are required to calculate sigma dot for this control volume. Sigma is the entropy production, and you are interested in the rate of that. Yeah. And actually, because sigma is used, there is no uppercase and lowercase sigma. Sigma is sigma. So that is the entropy production. And what you are required in this question is entropy production per unit mass. So you have to divide that by m, yeah, per kilogram. Yeah, per kilogram. So it also means that mass uh, must be given here. I'm just wondering if m dot will help you, because sigma dot divided by m dot, that cannot give you the rate at which entropy is produced. Okay, this is interesting. If you look at the unit here, um, if you look at the unit, he wants the answer in kilojoules per kilogram per Kelvin. Now this has no seconds in it. Yeah, this has no second. You have to be very careful with this. So actually, he should not have used the word rate here. This is wrong. Yeah, this rate is only correct if I have sigma dot. Sigma dot is the rate that looks correct, but the problem starts when you look at this m dot. So if I divide this by m, then I can call it rate. Yeah, sigma dot is the rate of production of entropy divided by mass. That's okay. But this will have units of what? This will have, because of the dot, and there is no dot in the denominator, so you must have seconds there. Because there is no seconds there, actually you are dividing by m dot. And I told you, if you start from the balance equation for entropy rate, you will have m dot, so you can only divide by m dot, just like this. So there is no difference between this m dot and that m dot. So actually you can think about rereading this question as determine the um, entropy produced within the turbine yeah, per unit stream. And that should not be a big problem because you can always start from mass balance, yeah, from chapter 4. Then you can rewrite an equation for the entropy balance, or to be very precise, entropy rate balance. Yeah. So you see, if you look at this, there's nothing fancy here. And this is the only unknown here, this, because everything else can be worked out. Now, how? How do you work this out? Q, this smallest one and smallest two, these are properties which you will have to work out from tables. Yeah? For water, you know that one state is in superheated, the other is saturated vapor, and you know from chapter 3 which table to look for. So if you look at those tables for water, you will get all the properties, and smallest one, smallest two is no exception. So the rest is pretty standard. Yeah, we have been solving these equations in chapter 4 and chapter 3. So this, I mean, you can do this very easily. Yeah, the only thing you need to watch out is the tables. So you see table A2, table A4. You know, you need table A2 because one of the uh, phases is saturated, and you need table A4 because one of the phases is superheated. And you can even see it in this diagram. Yeah? State 1 at which you start, this is state 1, this is state 2. So as I told you, this is superheated, so this is outside this vapor dome. And in state 2, you reach the boundary of the vapor dome. Yeah? So you know which table to look for in each case, and rest is just algebra. And I told you, as I told you, the quantity you are looking for is sigma dot divided by m dot, not sigma dot divided by m. And that's why the unit, you also know what unit to expect. So this was just a practice example for you. More important is to realize that the equation you wrote is for steady state. That's very important. That's why you have this 0. And you expect a term for the entropy transfer arising from heat transfer, entropy production arising from the irreversibilities within the system, and then entropy transfer arising from mass transfer. So now you can say that whenever you use the word entropy transfer, you have two sources for it: heat transfer, mass transfer. Okay. Now this example also looks very complicated because the claim is very interesting, but there is no magic here. Actually, there is no trick here. If you just follow all the bits and pieces with care, you can verify the claim of this inventor. So an inventor claims to have developed a device requiring no energy transfer by work. So he doesn't need any electrical energy or any mechanical energy. He just wants to use the natural steam available. Okay, there is no, I mean, there is no heat transfer needed. So neither heat transfer is needed nor work transfer is needed at the boundary. Uh, but he claims that he can still produce a hot and cold stream from a single stream of air and intermediate temperature. So look at this. What he claims is that he has a stream at some intermediate temperature, 70. So he says that, oh, give me a stream at 70 degree Fahrenheit and at that pressure, and I can turn this into two streams. One will be hotter than that, and one will be colder than that. So 70 degree Fahrenheit, 0 Fahrenheit, this is colder, definitely. And 70 degree Fahrenheit and 175 hotter. The pressure in this case, in both the cases, for both the outlets, yeah, cold outlet, hot outlet, the pressure is the same, 1 atmosphere. So it loses some of that pressure, actually most of that pressure, 5.1. And he claims that if you look at the boundary, for so doing, for splitting this stream into two streams at different temperature, he doesn't need any heat transfer from the surrounding. He doesn't need any work transfer from the surrounding. This claim looks to be unrealistic because you might expect, okay, how can I do this without requiring any energy, without requiring any work transfer, without requiring any heat transfer? But if you follow the basic principles, it will turn out that it's doable. There's nothing fancy. So this is the engineering model, of course. Work transfer is zero, heat transfer is zero. It's written in the question. And you assume the stream of air to be an ideal gas with constant pressure, with constant specific heat. I think this is also given somewhere. I think this is given somewhere. Where it's given? I think it's written there. Yeah. Evaluate the inventor's claim employing the ideal gas model for air. Yeah. Ignore kinetic potential energy. So everything is given to you. If you look at those tables for the ideal gas, if you take air and you assume it to be ideal, you can work out the um, specific heat at constant pressure, yeah, in BTUs. So maybe in this question you will need to use English units. This CP is given to you. So maybe if you look at this one, yeah, uh, what he guides you here is that if you look at table A20E for English, you will see some variation of CP. It's not that CP is constant. CP will have different values for different values of temperature, but but if you look there, the variation over a range of temperature from 0 to 175, and it's a large range, yeah, from 0 to 175 degree Fahrenheit, it will turn out that the value of CP doesn't change too much, so you can just take a constant value from that. Maybe you can verify this yourself, yeah. You will see that all the values will be very near 0.24, so why not assume that to be a constant for simplicity. So now how do you verify the claim? Basic principles. You need those three uh, equations from which we started this chapter, and then this section. Let me just rewrite down. You need mass balance, and to be very precise, you need rate, mass, rate balance. Sorry, mass, mass, rate balance, and then you need energy, rate balance, and then you need entropy, rate balance. Yeah, this is like some m dot equals to some other m dot, like 1, 2, 3, and so on. So this is your mass balance. Then you have the energy rate balance, this one. This is the energy rate balance. Yeah, you combine these two, and you know that if you assume the ideal gas equation, in the ideal gas equation, you can definitely, if you remember chapter 4, the energy rate balance has those enthalpies in it. Yeah. So the change of enthalpy for ideal gas has a simple expression. Yeah, because you assume Cp to be constant. Remember, Cp was relevant for entropy change, and if this was the change in internal energy, the corresponding constant relevant would be Cv. Here we have Cp because the energy rate balance involves delta H. Yeah? So the rest is standard. What you need to just watch out is this thing. I think there is some typo in this part. Yeah, I'll now tell you where's the typo. If you look at the description there, this is interesting. 60% of the mass entering the device exits at the lower temperature. Now, what does this mean? What this means that if this is M1 dot, if this is M1 dot, so 60% of that is here. 3 represents the exits. So M3 dot equals M1 dot times 0.6. So M2 dot will be M2 dot will be 0.4 because 0.4 plus 0.6 is 0. 1.0. M1 dot. So it should be M2 dot is equal to 0.4, M1 dot, M3 dot is equal to 0.6, M1 dot. So something must be wrong there. You see, M2 dot is 0.4. So this is wrong, this one. This must be M2, and that is correct. He has written M3 here as well, which is wrong. So just correct this to M2. And I think other than that, this is pretty standard. And you need to see how these values, if you look at these equations, let me just remove the clutter. So you must ask yourself, how do I verify this? This is automatically verified. Why? You don't even need to know M1 dot. Yeah. All you need to know is to look at the, and this has nothing to do with the claim. Yeah. This has something to do with the question given. So he gives you this information that 0.6 M1 dot is 0.6, 0.4. 0.4 times M1 dot is M2 dot plus 0.6 times M1 dot is M3 dot. So this is automatically satisfied. Now you need to see if his claim, if the claim of the inventor is right. And for that, you need to make sure that his claim does not lead to any contradiction of the remaining two equations, the energy rate balance and the entropy rate balance. So we start with the energy. The energy rate balance is this equation. Yeah? This equation. And on the left hand side, I have 0 because it's the steady state. So I just start with that. On the left hand side, I have 0. I have to make sure that if I plug all these different values, according to this picture, if at the right hand side I get a 0, then there is nothing wrong with his claim as far as energy rate balance is concerned. And similarly, I need to confirm that this claim does not lead to any contradiction with the entropy rate balance. So the entropy rate balance at steady state, left hand side is 0, steady state. Right hand side, will have a contribution from heat transfer, which must be 0 because he has said in the beginning there is no heat transfer. No work transfer, that is also 0. And the remaining terms are associated with mass transfer and entropy production rate. Yeah, so you plug that, just now this is not so simple. You need to use the ideal gas equation to calculate these quantities, S1 minus S2, S1 minus S3. You know how, I think in the last lecture, I told you how to calculate the difference of entropy between any two states for an ideal gas. And if you remember, this involved this logarithm of T2, T1, P2, P1, yeah, between any two states. So this part corresponds to S1 minus 2, this part corresponds to S1 minus S3, and we don't want to spend too much time on this working, because this is just an application of how to calculate the change of entropy. If you forget, let me just go back and just show you why this is not a big deal. I think we're done with that. What's this ideal gas? I don't remember if it was in this chapter. Yeah, these equations. You remember? It's these equations. The entropy change between any two states. Yeah, it depends on whether the state is described by temperature and specific volume. For that, you will need to use the first equation. You remember there were two equations, yeah? TDS equation 1 and TDS equation 2. Yeah. So the first equation will be relevant if the state was described by T and V. But if the state is described by T and P, then the entropy change from state 1 to state 2 is simply this term and this term. If you remember, these two formulas are actually, the second one is used in that example. So that's why I don't see any problem with that. For you, the take-home message is to know how to devise a strategy for solving this problem. And to verify, a claim by some inventor, you just need to look for contradictions. You have three rate balance equations, yeah? Mass rate balance, energy rate balance, entropy rate balance. You verify all those, and if none of this is violated, then you say, okay, no matter how preposterous that claim might sound, it is still correct. Yeah. So you can verify that. I think we can leave this example, 6.8. If you want, you can actually work this out. I don't see any complication in this. You have a cycle, of course. You have a cycle which has a compressor, two states given at the inlet and exit. Then you have an evaporator, again, two states. And then you have a condenser in which the refrigerant. So throughout this cycle, the refrigerant 134, I don't know. I think it's 134. It's being circulated in a cycle, so it returns to its original state every time at the end of each cycle, and it has to interact during this condenser with the air as well. So if you read this description carefully, you will come to know that, okay, state 1 and state 2, they are both superheated refrigerants, and in state 3 it comes to the other side of the vapor dome, compressed liquid, and in state 4 it goes to saturation. So you can actually figure out which table to look for each state. 4 states, you will need to find the right table, and you are supposed to calculate that sigma dot. Sigma dot is the um, production rate of the entropy. Of course, sigma dot. So I'm only now discussing the strategy. Sigma dot appears in the entropy rate entropy rate balance. You know, sigma dot is there. Similarly, there are terms for heat transfer. There are terms for mass transfer, and yeah, if this is steady state, the left hand side is 0. So the rest is just details. Yeah, I think those standard equations which I just showed you, and because you assume this refrigerant to be an ideal gas, the calculations are simpler. Yeah, these simple calculations are only possible because you assume the ideal gas model. There is one thing which is different in this example, if you want to work it out yourself, and that is the throttling process. So just let me highlight that, because that is the only thing which we have not been doing so far. The examples in chapter 4 and chapter 3 and chapter 5, it had other processes. So let me just find out. Okay, the refrigerant 22 enters the compressor. Yeah, pressure, temperature given. Then it's compressed adiabatically. So you know the process, adiabatic, no heat transfer, and temperature, pressure given again. So you just figure out, just note down that the temperature and pressure are used as a specification of the state. Then from the compressor, refrigerant passes through the condenser. Yeah, and this is the process. This one. This is the throttling process. Now, throttling process is not a quasi-equilibrium process, but you know from previous chapters that in a throttling process, the enthalpy doesn't change. So if you have, let's say, state 1 and state 2, and if the process between state 1 and state 2 is a throttling process, you just recall that, okay, the enthalpy will not change. Now, of course, in this question, we have to find out which states. So I think this state is throttling from 3 to 4. Yeah, this expansion from 3 to 4 is the throttling. So you just say, okay, H3 must equal H4, because we know that for throttling. I think this is the only thing which will be different from the other examples, and the rest is just an application of the entropy rate balance. And of course, you need to be aware. This is something which you need to improvise yourself. Although this chapter is about entropy, but you know that state 1 and state 2 are in superheated vapors. So you know which tables to use. You don't even need to use tables because of the ideal gas. If you assume the refrigerant to be ideal gas, you don't need to use tables. So you use just those equations. So okay, so you must now notice that the way I am glossing over these examples, the focus is not to solve these problems. The focus is just to recognize the importance of this entropy rate balance. That's the whole purpose of this discussion. Entropy rate balance, because you already know the other two rate balances, and it's just an appreciation of why entropy rate balance is so important, because most of the problems which involve irreversibilities cannot be solved without using this rate balance. Okay, I think that's enough for this uh, topic, and now we can move on to isentropic processes. You remember isentropic was the word used for any process during which the entropy doesn't change. So if you have a TS diagram, let's say TS diagram, so a process like this will be in, yeah, like going there or going down, up or down. Or you can also have a HS diagram, enthalpy. So again, these will be isentropic processes. So you look at TS diagram, 1 to 2 isentropic, 2 to 3 isentropic, and similarly for HS diagram. I think there was a name for HS diagram as well. Something started with MO, I think. Mo. I don't remember the exact name, but it was something familiar. Okay, I forgot the name. Um, okay, so if you use the ideal case model for any substance, you know how to write the entropy rate balance. So you write the entropy rate balance, and you know the process is isentropic. So if the process is isentropic, you know that the um, uh, the change in entropy must be zero. So if you express the change in entropy, you know this expression. I just showed you the equations for any ideal gas in which you use T and P as the state variables. The change in entropy will take this form. Yeah, you remember this S to zeroth. This S to zeroth was a specific expression, and we even have a table entry S0. So um, you can simplify the entropy rate balance for isentropic processes. So I think this doesn't need to be discussed in detail. You just and maybe I will provide these equations anyway. Yeah. So you should keep these diagrams in mind. Yeah, that anything like V, P, T, they can change the way determined by some processes. Yeah, they can change in any complicated manner. But if you just find out that okay, the entropy doesn't change, you have an isentropic process, and all these different expressions are simply um, simplifications. There is only one thing here which you might find different. We had this S naught of t thing. I think this was some integral, if I remember correctly, and this was then tabulated for different temperatures. Um, so if you assume isentropic process and you simplify the rate balance, you can even solve this equation for pressure, because the expression on the right hand side has logarithm of P2 and P1. So if you can invert everything here, you can write an expression for P2 in terms of P1. You will have this exponential, and I think this can be rewritten as P2 over P1. Just bring this P1 to this side, and because the exponent here has a plus and has a minus, so you can rewrite that as a ratio of two exponentials. Yeah, whenever you have the ratio of two exponentials, the exponents get subtracted. And I guess that this particular form of the exponential, so you have exponential of that S naught, which I already discussed. And this time you divide that S naught at some temperature, you divide this by the real gas constant, then you take the exponent, and this is because this will appear in some tables, so there is a name given to it. It's just called relative pressure. I think there is a name here, relative, yeah, relative pressure. Relative in the sense that you are calculating P2 over P1. So just to make sure that you follow the context, let me just write the crux of this matter. Let's say state 1 is one state, and then there is another state 2. And I will just use the TS diagram. Yeah, let's say I have a TS diagram, and I have the state 1 and the state 2. So I go this way, and in so doing, if I want to know the ratio of the two pressures, so P2 over P1, that ratio will have a simplified form which will involve the exponential of this S naught, which we already discussed. S naught is some complicated integral. So just to tabulate this exponential, you give this a name. Yeah? So instead of writing this exponential every time, you just refer to it as PR. Yeah? So because this is T2, so you have PR2, and then you have PR1. So this PR of T, which is the exponential of S naught of T divided by R, this is just given a name relative pressure, and this should not be confused with reduced pressure. Reduced pressure, they also use symbol R, but I think it's different. If you look carefully, maybe that R is. Um, does someone remember what was the notation for reduced pressure? It was P what? I think it was capital R. I think yes. The subscript there was capital R. This was not. This R did not represent the real gas constant, but the capital R was for reduced pressure, and the small r, now I realize why they had used capital R there, because small r will represent this relative pressure. And don't worry if you cannot actually connect all these bits and pieces, because um, I believe that if you are provided a table of different formulas, let's say this is formula, this is formula, this is formula, and let's say I provide these formulas, yeah, and I just write a description there, yeah. I don't see any reason why you cannot use these formulas to solve some particular problem. So more important for you are the assumptions. Yeah? So you must remember what assumptions you need in, for example, isentropic process, and you can rederive these formulas on the spot. So for example, this is a further simplification. If you assume specific heats to be constant, not to vary with temperature at all, then these formulas will get even simpler. uh, and yeah, and you can further get relationships between two temperatures, um, and the let's say the ratio of temperature can be related to the ratio of pressures by using the constant K. Remember, constant K was Cp over Cv, and you assume, normally Cp and Cv are functions of time, so K will also be a function of time. But what you assume in this section is that, okay, if Cp and Cv are constants, then K will also be constant, and that leads to these simple formulas. Yeah. And I think if you look at these results, this establishes something. We have already covered what is called the polytropic process. Polytropic process. I think this was in chapter 2, if I remember correctly. Polytropic process was when pressure and volume, or when pressure and specific volume raised to some exponent n is a constant. This is called polytropic. Yeah. Now, if you replace this n with not just any constant, but if you use k for that, k, remember, k is not just any constant, k is the ratio of Cp to Cv. Now, this is a special kind of polytropic process. Yeah, because polytropic process does not require this exponent to be equal to k. But if it is interpreted as, I think there in session 2 there was even a question where I specified that this exponent is k exactly. It was some MCQ, I think. Then this these equations from 6.43, 3.47, if you look at all these equations, of course, you assume constant specific heats, so K is assumed constant. It will turn out that isentropic, because this whole section is about isentropic processes. Yeah, so you have some observation here, which you can notice for future. Whenever you have isentropic process, and whenever that isentropic process is uh, involved for some ideal gas, so actually you just gather all the conditions. The first condition for the conclusion we have right now is that you have an isentropic process, yeah, because it's a requirement of this section, isentropic process. The second is that we have an ideal gas, because you need to remember these conditions. And the third is that you have a polytropic process. And I think with ideal gas, you also assume that K is constant. K is constant. Cp over Cv is constant. So then what you discovered is that in the polytropic process, um, will have this form. So um, so you can now flip this reasoning. Yeah, instead of knowing that it was an isentropic process, you can now use this observation in problem solving, that if you are given a process which is polytropic, and it turns out that it is not just any polytropic, but with that exponent equal to some k, and when you know that k is Cp over Cv, and then you also know that that is of course constant, because without that it's not a polytropic process, you can conclude that this must have been an isentropic process. So you are actually flipping the reasoning. Yeah. When you know it's isentropic, that's not rocket science. But when you know it's a polytropic process, and instead of n, this is the general case, you say, okay, it's not a general case, it's a special case. So I can conclude that it must have been an isentropic process. Now this will allow you to solve some problems, because maybe in that problem it is not explicitly mentioned that the process is isentropic. You have to infer it from this K. So I think that's the main message from this section. And these are different illustrations. Yeah, you have TS diagram, you have isentropic process, and you have to use one of those simplified equations. So that's not something we should worry about. I'm skipping many of these examples. Okay, so let me isentropic efficiency of turbines. I think this is also something which we can skip. We can skip this section, I think. So I am skipping this section because I'm sure there are not many time slots left. So of course this is a very interesting topic, but I similarly isentropic, this is, I'm also skipping that. Actually, this is just a part of that. So if we are skipping this section, we are automatically skipping if isentropic efficiencies of turbines, nozzles, compressors, pumps. So all they are actually subsections. Um, so for those who are curious, you start with the efficiency of a turbine or nozzle or pump or whatever, and you compare it um, with an isentropic version of that cycle. Sorry, it's not cycle. So let's say you have a turbine which will use real process, and you say, okay, you imagine all the processes to be replaced with isentropic processes, and then you just take the ratio. So this will be useful in some problem solving. Heat transfer and work and internally reversible. Now this is something which we need to discuss. This is, so I'm not actually skipping this. You just need to know that, okay, we have been talking about internally reversible processes. That is, it is that ideal process, which is also called quasi-equilibrium, just for record. And if you remember, I have been telling you that whenever you have internally reversible process, there is a specific relationship between heat transfer and entropy. Yeah. So entropy ds is related to heat transfer by this formula, yeah? Q dot over T, and if you write here internally reversible. Similarly, um, work transfer was also something related to, and if you remember, this had a consequence. This had a consequence that if you multiply that T ds by T, and then you integrate this, you should get the heat transfer. Yeah, you should get the heat transfer rate. Sorry, rate, because we are only integrating over S, so we will still have rate. Similarly, we have um, we have something, if you remember, for work transfer. So P dV, and if you integrate this, you will get work transfer. Let me just double check this. I think this Q dot is incorrect here. If I remember correctly, uh, this was W delta Q over T, and this was ds. Yeah, and now I can say that, okay, it's equal to Q. It's not Q dot. And similarly, analogous to this, we had this equation that delta W was P dV, and if you integrate, you get W. Yeah. So integral of pressure over volume gives you work. Integral of T over entropy gives you heat transfer. Both these are only true for internally reversible processes. Yeah. So that's the starting point. And if you now combine that, because there is nothing new for you, you already know that, you just combine those two concepts with steady state flow processes. So if you have flow process, um, which is internally reversible, plus it is steady state, so you can now imagine what can you write for heat transfer. Yeah, for heat transfer, you will have a 0 for steady state, and we are writing basically the entropy balance. This equation is the entropy rate balance. So Now we are writing heat transfer because this form of the equation uh, um, in takes into account the heat transfer as well. So you have a contribution from heat transfer, you have a contribution from mass transfer, you have a contribution from internally from irreversibilities. But because you assume internally reversible process, so that term is zero. Yeah. So just to step back, we start from the entropy rate balance. We assume internally reversible, so sigma dot is zero. And we assume steady state, so the left hand side is zero, and the rest is simple. And we also assume one inlet, one exit. Yeah, one inlet, one exit, because that's why you don't see those summations. If you simplify all this, you get a familiar formula. Now, this is something which you need to uh, notice, because so far um, we have not combined these three different concepts. We are combining internally reversible, we are combining steady state flow processes, and we also know that there is a flow process. So if there is a flow process, this also means that there is mass transfer. So you can expect m dot in your equations. Now that m dot, when that m dot divides your heat transfer rate, so you start with heat transfer rate, you divide that by m dot. So whenever you see this ratio, it should remind you that you are talking about some flow process. And if that flow process is internally reversible, this ratio will take a specific form, which is temperature times the difference of entropy between inlet and exit. Yeah. So this is something which you need to remember, which also means that if you now generalize this was a simplified picture for one step, for one inlet and one exit. Of course, in a general setting, you will have a boundary. You will have a boundary with many inlets and many exits. So you can use this simplified picture by replacing S2 minus S1 by ds. Yeah, so you have ds, and then you integrate from 1 to 2. Yeah, so from one state to state 2. So you can actually uh, the assumption here, remember, the assumption here uh, was a constant temperature. I think that's the main difference. It was a constant temperature for one inlet and one exit. But if that temperature is not constant, if between inlet 1 and exit 2, if the temperature varies, yeah, so that T is a variable, then you have to replace this simple formula by an integral. I think this should not be rocket science for you. This is very similar to this case. For example, if I say that pressure is constant, work done is simply for a compression, for expansion process. So it's simply pressure times change in volume. But if that pressure changes over volume, so what do? I replace this change with incremental change. Then P varies with V, so it's P of V, and then I integrate between two states. Yeah. So it's exactly this. Instead of S2 minus S1, because that's assumed constant temperature, I so you should see this as T as a function of S. Yeah? And that is, but don't forget the internally reversible thing. Yeah? Now, if you now compare this, I started this section. I just want to compare how I started and how this equation is different. It's very important. Otherwise, you don't know why we are discussing this in the first place. Remember, I started the discussion in this way. that I have Q, and that Q for internally reversible process is simply the integral of T ds. Remember, I used ds, the upper cases, not the smaller cases. So if I divide this by m, this uppercase s will become smaller as specific entropy. And now dividing by m doesn't make sense because I'm talking about a flow process. So in a flow process, I will have mass flow rate m dot. So dividing by m dot will be something I'll be doing because I'll be writing some entropy rate balance, and entropy rate balance will not have m, it will have m dot. So if I divide by m dot, then this integral will not give me q heat transfer, but heat transfer rate, because rate divided by rate, yeah, so this, the effect of this dot and this dot disappears, and you basically have the same equation from state 1 to state 2. So I would call this equation as a flow version of this equation. You're very familiar with this 1 to 2, and you're calling it Q. So just instead of re-deriving this, you should be able to use simple reasoning. If I have Q dot and if I divide this by M dot, nothing will change on that side. No, this will, sorry, this will just become small s because you're dividing by mass. And because both Q and mass are derivative dotted, so you will not see any differentiation on the right hand side. Otherwise, you should see dt as well. For example, if this if this dot is missing, yeah, then you should expect some dot there as well, yeah, and we don't see that, yeah? So it's actually m dot. Now this whole reasoning can be repeated for work transfer, yeah. So just like we had an expression for q dot over m dot for flow processes, we will have an expression for w dot over m dot, yeah, work transfer over m dot. And because you are using one inlet, one exit control volumes, so you will again start with that. First, you start with energy rate balance. Yeah? For energy rate balance, if this looks confusing to you, let me just write 0 here and take this to the other side. So there it will be minus w dot cv over m dot. Now I multiply everything by m dot, so this will disappear. This will disappear. You will have m dot here, and you will have m dot here. Now, if you recall the energy rate balance, m dot had to multiply the change in enthalpy, the change in kinetic energy per unit mass, and the change in potential energy per unit mass. So you see, it's that same equation, and there, if you remember the energy rate balance, you had, in addition to it, q dot minus w dot, both cv, and then this was 0 because steady state. So all he has done is to take this minus w dot to the other side and divide everything by m. So now you can see that this equation doesn't look very different. You just have transported the work transfer to the other side, divided everything by m dot. So you start from the energy rate balance, and then you incorporate the result from the previous section. The result was that if it was internally reversible, then Q dot over M dot will have a specific expression. So remember, writing this equation does not assume any internally reversible process. It is just the energy rate balance. Energy rate balance. What are you assuming in this equation? Let me just list it. The assumptions in these equations are steady state. Number two, one inlet, one exit, one inlet, one exit. Yeah, that's all. But if you now combine this with the assumption of internally reversible process, then this will not change. You just have to write internally reversible as a subscript. This will not change because this is a change of properties. Change of property doesn't care the detail about the detail of the process. This doesn't change property. This doesn't change property. So the only thing that will change is this term. You know, if you take this ratio to be for the internally reversible process, that has a specific expression, integral dds. That's exactly what we just saw there, question 6.49. Yeah, this ratio for internally reversible will be integral of TdS. So that means that we can rewrite the energy balance in this form. And if you remember, we had two versions of the TdS equations. Yeah, one was starting with du and one was starting with dh. So the one with du was, I think it was du plus pdv, and the one with dh was with a minus sign vdp. So if you take this second case and you take that as a starting point, integrate both sides, you will get the change in enthalpy, integral of specific volume over pressure, and you can now replace this integral. Now this integral was a consequence of internally reversible process, and then you simplify this integral with this expression, because you want to write an equation which has no entropy in it. We want to express entropy in terms of other variables. And now if you look at this 6.51a, what do you see here? You have an expression for work transfer for an internally reversible process, and the right hand side does not have entropy in it. There is no entropy. All you see on the right hand side is specific volume, pressure, kinetic energy, and potential energy. Now you think about this. In the previous section, when we wanted to have this ratio, let me just declutter everything, and I want you to compare these two cases. It's important. Okay. Because this section is focusing on heat transfer. We know heat transfer has associated with it entropy. So entropy transfer arises from heat transfer. So that's why we would like to express the heat transfer divided by m dot as an expression which involves entropy and temperature. You associate temperature and entropy with heat transfer. But when you want to write similar expression for work transfer, now work is organized form of energy transfer. You would not like to see entropy there. So you express entropy in terms of quantities. If you look at everything on the right hand side, you associate volume, specific volume, pressure. You associate this with the expansion work, with the expansion work. Now this is if you have a change in kinetic energy, if you have a change in potential energy, you know change in kinetic energy and change in potential energy, because they are also organized forms of energy, so they can be associated with with work transfer. So that's the purpose of this derivation. And if you assume that in many cases, just like turbines, compressor, pumps, in those applications, the change in kinetic energy and change in potential energy is insignificant. So you have a simplified picture. If delta Ke and delta Pe is zero, as is assumed for turbines, compressors, and pumps, you have a simplified formula for work transfer rate, work transfer per unit mass, work transfer per unit mass, because dot here and dot here will remove the rate from it. So I can now rewrite these two formulas here as in a box. Just as a reminder, we discovered two formulas, 1 to 2 TDS and 1 to 2 VDP. Yeah, of course, with this assumption. 1 to 2 TDS is Q dot over M dot for internally reversible process. And with the minus sign, integral VDP is W dot CV over M dot, again for internally reversible. Don't miss out the minus sign, okay? This minus sign is a consequence of the fact that work done, when you write W, you mean work done by the system. And work done by the system means that energy is leaving the system. And Q, because Q, when we write Q, we mean heat transfer into the system. So that's why there is a plus. And a simplified version of this will be, let's say I start with this equation and I assume that the specific volume V is constant from state 1 to state 2. So that will be taken out as a constant, and that will be P2 minus P1. P2 minus P1 with a minus sign. That's a simple version. You assume V to be constant and so on. Okay. Polytropic process. I think polytropic process is just remember that, okay, we have PV to some constant equals another constant, and you choose different values of n for different processes. So yeah, because now you know a simple expression for the work transfer per unit mass for any flow process which is internally reversible. So remember, this expression requires you to remember that it's okay, it's for a flow process and it's for internally reversible process. So you know that, okay, when you want to integrate specific, previously we have been doing this PdV. Now you want to do VdP. Now, whether you want to integrate P with respect to V or whether we want to integrate V with respect to P, you still need some model which assume a specific relationship between P and V. You need a PV diagram. So PV diagram, area under P, and if you have a PV diagram, area under P will be integral PdV, and area above P, yeah, within some limits, will be integral VdP. And you can take advantage of this relationship to simplify this. तो आपको पता होगा उसी तरह से हमारे पास सिंपल फार्मूलाज आ जाएंगे कि when n is equal to 1, so you get some logarithmic formula, and if n is not equal to 1, you get some other form. अच्छा, अब यहाँ पे आप, आई डोंट नो, आपने एक चीज नोट की है कि नहीं, जब हमारे पास, क्योंकि अब ये एक जहन में क्वेश्चन जरूर आना चाहिए ना, हम जब वर्क को पहले डिस्कस कर रहे थे पहले चैप्टर में, सो वी हैड this formula. We had this formula PdV from, let's say, one. This was our work transfer. And now suddenly we are using VdP, of course, with a minus sign. So can anyone try to explain why we have this difference? Of course, ये सारी mathematics और derivation तो आप करने के बाद आपको समझ आ ही जाएगी. But without that, if you just remember the title of this section, this was the expansion work, if you remember. Yeah, if dV is positive, you call it expansion work. If dV is negative, you will call it compression work. Now, whether it's expansion work or compression work, you imagine a system which is expanding or compressing. None of these are classified as flow processes. Yeah, flow process is used for control volumes. So let's say you have a control volume. This is a boundary. The boundary, this is an abstract boundary, and you have some matter in the form of fluid entering and leaving. Now it's the fluid which enters and leaves. The system doesn't move. That's the point. The system doesn't move. So when the system doesn't move, the system neither expands nor compresses. So definitely dV is zero. Yeah, there is no change in volume. So what does it mean? Because we are talking about, it's not because of control volume, we are talking about a flow. Yeah, I don't want to say that control volume cannot expand. Control volume can expand, but you will not call it a flow process then, because we are focusing on a flow process. For a flow process, only the pressure can vary from inlet to exit. So let's say you have stream entering at one pressure, steam leaving at another pressure. Between these two pressures, there is no change in volume. Yeah. When I say there is no change in volume, I mean expansion. So there is no expansion going on. So from P1 to P2, specific volume can change because you cannot guarantee volume to be the same everywhere. So in that process, for example, this V is a property of this stream. So if fluid enters at P1, and it will have some specific volume P1, and if it leaves at another pressure, in so doing, the fluid could have changed its specific volume. So if it's a compressible fluid, you cannot expect it to have the same specific volume. So which means that specific volume can change with pressure, and when you integrate that with respect to that specific volume with respect to pressure between two states, that will give you the work transfer associated with a flow. So it's the flow process which forces us to integrate V with respect to P and not P with respect to V. That's a quick way of remembering it. Okay, I think we are done. So let's close this now. If you have any questions, I can wait for that. Let's close this first.